Welcome to lecture 32. This is on Green's theorem, the flux form in 2D. And so we're going to basically illustrate Green's theorem on a connected, not simply connected region. So this is more or less following up from the previous lecture. The material being covered here is from reading assignment 4, section 4.1.3. And more or less the concepts visualization skills are to introduce a cut in an annulus and compute the flux from an annulus. As usual, the second slide just an outline of what is to follow, so we'll just skip over this and move on to the next slide. So the problem statement is to compute the flux exiting the boundary of an annulus using Green's flux theorem and show that the right-hand side and left-hand side give the same results. We're going to assume a vector field F in region R given by the expressions that are shown, one for F and one for R. They're basically here. And so we start basically by drawing a picture of the region as described, which basically involves a region between a circle of radius 4 and a circle of radius 1. So this is 1 and this is 4. And so this is effectively the problem that we're looking at. So this problem, as shown here, is basically not a problem that we're able to solve using Green's flux theorem. And so the simplest solution is to introduce a cut to make the region simply connected. And so this cut is shown here, circled in red, right? And so from the previous lecture, we showed that we could essentially draw a contour consisting of 4 segments that basically enclose the region, in which case, in this case, we are able to use Green's flux theorem. All right, so we're going to compute the flux using the left-hand side and right-hand side of Green's theorem. I've basically shown the picture for the vector field and all the salient things of interest to us in computing the flux. So for example, N1, which has to be pointing outwards, we're going around the closed contour in a counterclockwise direction. Again, always looking to your right. So N1 is pointing outwards on this outer circle. Moving in this direction, it'd be pointing in this direction to your right. Going in this direction, it's pointing to your right, which is in this direction. And finally, along the last part of the segment, the 4th segment is pointing to your right, which is this one. So you got 4 individual segments, and the direction vectors normal to the contours are basically provided. And this in red is the vector field. If you want to look at it, you can. It's accessible at the URL that's sort of shown here. All right, so we're going to apply Green's flux theorem using the figure to the left. And so on the left side, it's a closed contour integral of f dot ns ds, right? And this is equivalent to the divergence of the vector field integrated over the area enclosed. And that's equivalent to df dx plus dgy dA, where f is this term here and g is this term here. All right, since this contour basically consists of 4 segments, we've written it out as follows, like this. And also we make note of the fact that when you go in this direction and then in this direction, you get cancellation taking place because the normals are in opposite directions but the same. So that means, for instance, the fact that this f dot ns3 ds equals minus f dot n of force ds, when we add this term and this term, essentially these two cancel. And so we're just left with this integral and this integral. And so that's basically the objective then, is to compute this integral and this integral. Alternative, if you wanted to, you could reverse the direction of C2. So instead of basically going in this direction, you could go in this direction for this particular interval. And that would mean this becomes a minus C2. But if you change the direction on the contour, then this sign has to change with it as well. So this would become minus f dot n2 ds. Even though you're keeping n2 in this direction, you'd have to invert the sign. So you put a minus here. So this is effectively the calculation that we're going to be performing. All right, so we need to basically figure out what N1 and N2 are. So we need, first of all, a position vector for contour C1, and we need a position vector for contour C2. For the position vector for contour 1, this will be 2 cos theta, 2 sine theta. And so this represents basically the outer circle. And so this is in a counterclockwise direction. And so we have to make sure that as theta advances from 0 to 2 pi, basically we are following the trajectory. It's mapping out the points on the exterior contour in a counterclockwise direction. And this, in fact, is the case here. But we want nsd1 ds, and so from previous lecture, we found that this is nothing more than y dot minus x dot d theta. This is 2 cos theta, 2 sine theta, and this, in fact, is pointing outwards. You can confirm it's pointing outwards, right? So this will mean to take the derivative of this, which is 2 cosine theta, plug it in here, and to take the derivative of this, which is minus 2 cos theta times negative, which becomes 2 sine theta. So that more or less is nsd1. For nsd2, we're talking about a radius now, which is 1, which is on the inner contour. But in this case, we're going this way around. And so going from theta 0 to 2 pi, that position vector should be moving in this direction. And turns out this is the correct assignment for sines. Cos theta minus sine theta. Again, you can determine what the normal to that contour is. It's just y dot minus x dot as before. And this turns out to be minus cos theta sine theta d theta. And the direction of this is consistent with the direction you see here. So effectively, we now have ns1 ds and ns2 ds. Next step basically is to substitute the values for x and y for the two contours, right? So that this now becomes parameterized in terms of theta. And so the final integral would be just the sum of this flux, the sum of this flux. And so f dot n d1s, this is the flux that you would get after substituting 2 cos theta and 2 sine theta for x and y into the vector expression you see here. This 2 cos theta, 2 sine theta d theta, that's basically the expression for ns1 ds1. And similarly, for the second contribution here, f dot n2 ds, this is the vector f, and this is the vector n2 ds. So the rest is just integration. If you do the calculations, you'll find you get an answer of 15 pi divided by 2. All right, so now let's basically redo the calculation on the right-hand side of Green's theorem. Again, this is the field vector that we're dealing with. So we need to take the partial of this f with respect to x and add it to the partial of g with respect to y. If you do that, you'll end up with x squared plus y squared dA. So the next thing basically is to do this double integral. And given that it's circular, it would be appropriate to solve this integral in polar coordinates. And so in polar coordinates, the transformation is x equals r cos theta, y equals r sine theta. And the region basically is bounded by a circle of radius 1 and a circle of radius 2, and theta spans from 0 to 2 pi. So this is the boundary on the integrals, 1 for r, 1 for theta. This is the transformation. And of course, from this, you can compute the Jacobian. And so dy dx maps over to r dr d theta. So this expression in polar coordinates just becomes r squared, r dr d theta. First integration is with respect to dr, between 1 and 2, and theta is between 0 and 2 pi. If you follow through and do this calculation, you get 15 pi over 2, which basically says that the right-hand side is in agreement with the left-hand side. So clearly we have shown here, with the technique that was basically developed in the previous lecture, that in fact, in this case where you start with a not simply connected region, that by introducing the cut, we can still employ Green's Flux theorem and basically see agreement between the left-hand side and the right-hand side. So that concludes lecture 32. Thank you for listening.